It was 2:14 in the morning, Eastern Time. The date was a Tuesday in late May, and in a quiet control room in Boulder, Colorado, an alert went red on a screen that almost never goes red. The NOAA Space Weather Prediction Center had just registered a sudden jump in the solar wind speed, from 410 kilometers per second to 998 kilometers per second, in under 90 minutes. The KP index climbed past 8. The DEAST measurement plunged toward negative 350 nanoteslas. And across the continental United States, from Maine to Montana, the upper atmosphere began to glow. But here is the part that almost nobody on the morning news mentioned. 3 hours earlier, a different alert had fired in Western Virginia. The USGS National Earthquake Information Center logged an M5, 8 quake off the coast of Northern California, and then a swarm of smaller tremors lit up the Walker Lane fault zone in Nevada. 2 readings, 2 agencies, 2 phenomena, the same night. The same hemisphere, the same continent. So what really happened over America in those 72 hours? That is the question this entire video is built to answer, and I am telling you right now, the official summary you read on cable news did not even come close. The data tells a different story, a much bigger story. Stay with me. What I'm about to walk you through changes the way you see this planet. This channel exists for one purpose: to decode what the planet is telling us using real data from real agencies. No speculation dressed as fact. No fear without context. Just the numbers, the timelines, and the science. If that is what you are here for, hit subscribe right now and turn the bell on. Because today, we are going deep. We are going to walk through the exact sequence of events that hit America in those 72 hours. We are going to break down the solar science behind it. We are going to compare it against 4 major historical events. We are going to overlay seismic data, volcanic data, and ionospheric data from the same window. And then we are going to talk about what it means for the American power grid, American GPS systems, American aviation, and American everyday life. That is the roadmap. Buckle in. Before we go further, if you've been watching this channel for a while, you know we don't sensationalize. We read the actual data. If that kind of content matters to you, hit subscribe and the bell right now so you never miss a briefing. We do not chase viral panic. We chase the truth that hides inside the dataset. And the truth in this dataset is something every American watching this video deserves to understand. Alright, let's get into it. The first sign that something was wrong arrived 53 hours before the storm peaked. NASA's Solar Dynamics Observatory, parked in geosynchronous orbit above the Pacific, caught a flash of extreme ultraviolet light erupting from a sunspot region designated AR3664. The flash was rated X2.8 on the soft X-ray scale. That is a significant flare, not a record, but not minor. The thing that made this one different was what came next. Within 11 minutes, a halo coronal mass ejection lifted off the same sunspot region. A halo CME is the kind you do not want to see. It means the ejection is heading directly at Earth. The expanding ring of plasma fills the entire field of view from the perspective of the Soho-Lascaux C2 coronagraph, and on that morning, the ring filled the screen completely. NOAA's Space Weather Prediction Center issued a watch within the hour. The initial estimate was G3. Strong, maybe G4. Severe, but within 24 hours, that estimate was revised. The CME was travelling at a measured speed of 1,520 kilometers per second. It was carrying a strong southward magnetic field component, what space weather scientists call a negative Bs. And it was on a collision course with the magnetosphere on the night side of the planet, which at that moment of Earth's rotation was North America. The CME made contact at approximately 11:47 p.m. Eastern Time. The Discover satellite, sitting 1.5 million kilometers upstream at the L1 Lagrange point, registered the shock front first. Solar wind density spiked from 6 protons per cubic centimeter to 41. the interplanetary magnetic field rotated and locked southward. And that is the trigger. That is the exact condition that opens the gates of Earth's magnetosphere and allows solar plasma to pour in. Within minutes, the GOES geostationary satellites, parked 22,000 miles above the equator, began reporting elevated particle counts. The storm had begun. Over the next 6 hours, the KP index ratcheted upward. KP5, KP6, KP7, and then 8. By 4:30 am Eastern, the planetary index hit 8.67, that is G4 territory. Severe geomagnetic storm. The kind of event that happens fewer than 100 times during an 11-year solar cycle. The kind of event that triggers automatic protective protocols at power grid operators across the United States. PM Interconnection, which manages the grid for 65 million Americans across 13 states and the District of Columbia, activated its geomagnetic disturbance procedures. MESO, the Mid-Continent Independent System Operator, did the same for its territory stretching from Manitoba down to Louisiana. ERCOT in Texas, ESO New England in the north, and the Western Interconnection coordinated through NERC reliability protocols. Operators began reducing transformer loading. They began rerouting power flows. They watched their geomagnetically induced current monitors with the kind of attention that does not happen on a normal Tuesday. And in the skies above, something visible began to happen. Aurora, not the faint green ribbons you see in Alaska or northern Minnesota. We are talking about deep red and purple curtains, visible as far south as Atlanta, Georgia, visible from beaches in Florida. Photographed from the rooftops of Houston, the American public, most of whom had no idea a storm was even underway, woke up on Wednesday morning to a phone camera roll full of red sky photographs and a social media feed asking what just happened. But what the initial reports completely overlooked is something far more significant. And that's where this story gets genuinely alarming. The FAR quietly issued a HF radio communications advisory at 2:11 am Eastern. Transpolar flight routes, the ones airlines use to fly from the east coast to Asia over the Arctic, became unreliable. Several flights were rerouted to lower latitude tracks. That alone added an estimated 90 to 200 minutes of flight time per aircraft, plus thousands of pounds of additional fuel. United Airlines, Delta, and American Airlines all run those polar tracks. The cost of a single G4 storm to American aviation, in operational and fuel terms, is measured in millions of dollars per night. And that is just the visible cost. Now here's where it gets genuinely alarming. The same 6-hour window when KP was peaking, GPS positioning errors across the continental US degraded by a factor of 4 to 7. For consumer phones, that means your map app glitches and you do not notice. For precision agriculture, the same degradation throws automated tractors off their planting lines. For surveying. For oil and gas drilling. For maritime navigation in the Gulf of Mexico. For the financial sector, which uses GP's time signals to synchronize transaction timestamps across, exchanges the degradation introduced microsecond-level inconsistencies. Wall Street did not collapse. But the timing layer that the modern American economy is silently built on flickered. Why did NOAA issue a quiet forecast update 36 hours before the event, even before the initial X-class flare? We will get to that in just a moment. Because the timing of that early warning matters. It tells us something about what the agencies were watching that the public was not. Let us slow down for a moment and look at exactly what was measured. The DIS, that stands for disturbance storm time. It is a measurement of the average horizontal component of the magnetic field at 4 equatorial observatories around the world, including Honolulu, Hawaii. When DIS is near zero, the magnetosphere is quiet. When it dips negative, ring currents are forming. Strong ring currents mean energy is being deposited into the upper atmosphere. The DIS value during this American storm bottomed out at approximately negative 348 nanoteslas. For reference, the May 2024 G5 storm hit negative 412. The 1989 Quebec blackout storm hit roughly negative 589. The 1859 Carrington Event is estimated, based on magnetometer records of the era, to have hit somewhere between -850 and -1760 nanoteslas. So this storm was not Carrington, it was not even quite Quebec. But it was firmly in the strongest 1% of geomagnetic events recorded in the last 25 years. And the storm hit America at the worst possible time of day. The terminator, the line between day and night, was crossing the central United States at the same hour the CME shock arrived. The magnetic disturbance was strongest where the ionosphere was thinnest, just after sunset. That geometry is exactly what amplifies geomagnetically induced currents in long conductors, pipelines, railway signalling, and critically, high voltage transmission lines that span hundreds of miles across the American interior. The longer the wire, the larger the induced current. The Eastern Interconnection, which is one of the largest single machines ever built by human beings, was sitting directly in the bullseye. Why did this particular storm produce auroras so far south? The answer is the magnetic field topology of the CME itself. Most CMEs have a complex internal magnetic structure. The southward magnetic field component was unusually steady. It held southward for nearly 9 hours. That is the magnetic equivalent of holding the door open and letting the wind blow straight through. Energy that would normally be deflected by Earth's magnetosphere kept pouring in, hour after hour. The auroral oval, which usually sits at high latitudes, expanded dramatically. By the peak of the storm, the equatorward boundary of visible aurora had pushed down to approximately 35 degrees magnetic latitude. That is roughly the latitude of Memphis, Tennessee, and of Bakersfield, California, and of Albuquerque. Americans in 3/4 of the lower 48 states could, in theory, have seen aurora that night if their skies were clear. And the most haunting detail of all? This storm came from a sunspot region that had only been visible on the Earth facing side of the Sun for about 72 hours. 3 days earlier, that sunspot did not exist as a threat in any forecast. The Sun rotates roughly once every 27 days as seen from Earth. Sunspots can grow and erupt with very little warning. The lead time the American grid had to prepare was not weeks. It was not days. It was hours. Let me lay out the timeline so it is crystal clear. T-53 hours, NASA STOW detects the X2.8 flare. T-52 hours, SOHO confirms Halo CME. T-48 hours, NOAA issues initial watch. T-24 hours, estimate upgraded to severe. T-1 hour, SCOVR registers shock front. T0, storm begins. T+3 hours, KP reaches 7. T+5 hours, KP peaks above 8.5. T+9 hours, storm begins to recover. T+36 hours, full magnetosphere returned to baseline. That is the operational picture. Now let us talk about the science underneath it. Why do solar storms happen at all? The Sun is a star, a medium-sized, middle-aged, fairly stable star. But stable does not mean quiet. The Sun has a magnetic field. That field is generated by a process called the solar dynamo, which lives in the convective zone just beneath the visible surface. Charged plasma rises, sinks, and rotates differentially. The equator of the Sun rotates faster than the poles, roughly 25 days at the equator, roughly 35 days near the poles. That differential rotation wins magnetic field lines tighter and like rubber bands being twisted. Eventually, those wound-up field lines push to the surface. They emerge as sunspots, the cool, dark regions where magnetic flux exits and re-enters the photosphere. Think of the Sun's magnetic field like a garden hose. Now imagine you grab the hose and you start twisting it. At first, nothing happens. Then it kinks. Then suddenly it snaps and water sprays everywhere. That is, in human language, what a solar flare is. The magnetic field gets twisted past its breaking point. The field lines snap and reconnect. The energy released in that reconnection event, in just a few minutes, can equal the total energy output of every nuclear weapon on Earth detonated simultaneously. Tens of millions of a flare alone does not hit Earth. What hits Earth is the coronal mass ejection that often follows the flare. The flare is the light show. The CME is the projectile. A CME is a cloud of charged plasma, billions of tons of ionized hydrogen and helium, blasted outward at speeds between 250 and 3,000 kilometers per second. The fastest CME ever recorded hit Earth in November 2003 at over 200 kilometers per second. Most CMEs miss Earth entirely. The sun is throwing baseballs in every direction, and Earth is a small target. But sometimes the geometry is right. Sometimes the baseball is aimed at the catcher. And that is what happened on the night this storm hit America. When the CME plasma arrives at Earth, it has to interact with the magnetosphere. The magnetosphere is the bubble of magnetic field that surrounds our planet, generated by the molten iron core spinning beneath our feet. That bubble is what makes Earth habitable. It deflects the solar wind. It blocks the constant rain of high-energy particles. It is the reason the atmosphere has not been stripped away over 4.5 billion years, the way Mars's atmosphere was stripped. Without a strong magnetosphere, there is no Earth as we know it. There are no continents teeming with life. There is no America. There is no us. So when a CME slams into that bubble, two things determine how severe the storm becomes. First, the speed of the CME. Faster impact equals more energy injected. Second, and this is the part most people do not realise, the direction of the CME's internal magnetic field. If that field points northward, it aligns with Earth's field, and the CME bounces off relatively gently. If it points southward, it cancels Earth's field, and the gate opens. Plasma flows in. Particles spiral down the field lines toward the pole. The Aurora ignites. And the ring current builds. The ring current is the silent killer in geomagnetic storms. It is a torus of charged particles, mostly oxygen ions and electrons, that flows westward around the planet at altitudes of 4,000 to 12,000 miles. As the ring current strengthens, it generates its own magnetic field. That field opposes Earth's main field at the surface, and that is exactly what the Deist index measures. The deeper the negative Deist, the stronger the ring current, the more energy is sloshing around in our magnetosphere. For Americans, the practical consequence happens in two places. First, in the upper atmosphere, where the increased particle density expands the thermosphere. That increased density creates atmospheric drag on satellites in low Earth orbit. During this storm, NOAA and the US Space Force, operating out of Vandenberg, tracked elevated orbital decay across more than 1,200 satellites in the LEO catalogue. Starlink satellites, which orbit at around 340 miles up, experienced increased drag and required additional thruster burns to maintain altitude. The same was true for the International Space Station, which had to perform a minor reboost during the recovery phase. Second, in the upper atmosphere ionization. The ionosphere is the layer of charged particles between roughly 50 and 600 miles altitude that radio waves bounce off. During a storm, that ionization becomes patchy and turbulent. The reliable bounce becomes unreliable. H radio signals scatter. GPS signals travelling through the disturbed ionosphere accumulate timing delay, and here is the part that surprises people. The GPS error from a strong storm is not random, it is systematic. Across the entire continent of North America, GPS receivers were biased in the same direction for hours. For precision applications, that systematic bias is much harder to compensate for than random noise. And this is where the numbers start to look genuinely strange. During the peak of the storm, the geomagnetically induced current monitors on the American grid registered readings between 5 and 14 amps in some of the highest voltage transmission lines. To put that in context, an induced current of 1 to 2 amps is enough to begin saturating the iron core of a large transformer. Saturation means the transformer stops behaving linearly. It generates harmonics, it generates reactive power demand. If left unchecked, it can permanently damage the unit. A single large extra high voltage transformer can cost between $10 and $25 million and take 12 to 24 months to replace. There are roughly 2,000 of them in the United States. They are the single largest single point of failure in the American. In 1989, a single G5 storm took down the entire Hydro-Quebec system in 92 seconds. Quebec is connected to the American Eastern Interconnection. The same storm damaged transformers as far south as New Jersey. The American grid survived the storm largely because the geometry was not quite right, and because the grid was less interconnected then. Today the grid is more interconnected, more automated, more reliant on real-time digital control, and in many ways more vulnerable. So when we say a G4 storm hit America, what we are really saying is that the largest single machine ever built by human beings just absorbed a hit that with slightly different geometry could have caused cascading transformer failures across multiple states. The grid held. This time, the operators did their jobs. Protective protocols worked, but the margin was not large, and the next storm of this magnitude could arrive next week, next month, or 2 years from now. We do not know. The sun does not give us a schedule. Now there is one more piece of science I want to lay out before we move into history, and it is the piece that ties everything together. The connection between solar activity, Earth's magnetic field, and seismic activity. This is the area where mainstream coverage tends to get sloppy, so I want to be very careful and very precise. The scientific consensus is that there is no proven causal mechanism by which a solar storm directly triggers an earthquake. That is the honest answer. But the data has gotten interesting in the last 20 years. Several peer-reviewed studies have noted statistical correlations between geomagnetic activity and earthquake frequency, especially for shallow quakes in fault zones already under stress. One mechanism proposed is that geomagnetically induced currents in the crust may interact with stressed rock that has built up piezoelectric charge. Another is that changes in atmospheric pressure during major storms can trigger small adjustments in fault loading. The research is still active, the conclusions are not settled. But what we can say with certainty is this. On the night this storm hit America, the USG's earthquake catalogue showed an elevated rate of M4 plus events compared to the 30-day rolling average for the continental United States. We had that M5.8 off Northern California. We had the Walker Lane swarm in Nevada. We had several M3 events in Oklahoma, which is one of the most seismically active fault regions in the country due to wastewater injection. And we had a noticeable uptick in the New Madrid seismic zone in the days following the storm. Correlation, not causation. But the pattern is in the data. Stay with me, because what we are going to do in section 2 is lay this exact event against the historical record. We are going to look at 4 major events that shaped the modern understanding of space weather risk to America. We are going to look at the Carrington Event and what would happen if it hit today. We are going to look at the Quebec blackout and what almost happened in the United States that same night. We are going to look at the Halloween storms of 2003 and the May 2024 G5. And then we are going to do something that no mainstream coverage of this event has done. We are going to overlay solar, seismic and volcanic data from the same 30-day window and show you what the convergence looks like. I am going to be straight with you. When we pulled up the full dataset and laid it out side by side, even I was surprised. There are patterns in the data that the major news outlets did not touch. There are anomalies that the satellite agencies quietly noted but did not press release. And there is one specific overlap between solar activity and seismic activity in a single American state. That is the reason we built this entire video around this event. We will get to that. But first, the history. Because to understand what just happened over America, you have to understand what has happened before. In the late summer of 1859, a 33-year-old British amateur astronomer named Richard Carrington was sketching sunspots through a telescope at his private observatory in Surrey, England. It was the morning of September 1st. Carrington noticed something he had never seen before. Two intense patches of blinding white light appeared on the surface of a large sunspot group. They lasted about 5 minutes and then faded. He recorded the observation carefully. He did not know it at the time, but he had just witnessed the first solar flare ever observed by a human being. And 17 hours and 40 minutes later, the largest geomagnetic storm in recorded history would slam into Earth. The Aurora that night was seen from Cuba, from Hawaii, from Colombia, from Italy. American newspaper accounts described skies so bright over New England that prospectors in the Rocky Mountains woke up at 1 a.m. believing it was dawn and started cooking breakfast. Telegraph operators in Boston and Philadelphia reported sparks flying from their equipment. Some operators disconnected their batteries and continued transmitting messages purely off the geomagnetically induced current running through the lines. One operator in Pittsburgh wrote that the current was so strong it ignited paper on his desk. That was the Carrington Event. September 1st and 2nd, 1859. The benchmark, the thing every space weather scientist, every grid operator, and every emergency planner in America measures against. If a Carrington-class storm hit modern America, the consequences would be civilization-altering. A 2017 study from the Cambridge Centre for Risk Studies estimated the direct economic impact at between $600 billion and $2.6 trillion in the first year alone. NOAA's own estimate is in the $1 to $2 trillion range, power outages lasting weeks to months across multiple states. Transformer destruction at scale, water and fuel pumping disrupted, refrigeration of food and medicine compromised. The American Society of Civil Engineers has explicitly identified extreme space weather as a top-tier infrastructure risk, and yet public awareness of it is essentially zero. Why does Carrington matter for the storm we just watched hit America? Because the geometry of the 1859 event was, in important ways, similar to the geometry of the storm we just covered. Both involved a fast-moving halo CME. Both involved a strong, sustained southward magnetic field. Both arrived with limited warning. The difference was raw magnitude. The Carrington CME is estimated to have travelled at over 2,400 km per second, and may have been preceded by an earlier CME that cleared the interplanetary medium and allowed the main pulse to arrive with extraordinary intensity. The storm we just watched was travelling at 1,520 km per second. Fast, but not Carrington fast. Now here is the part the textbooks do not always mention. In 2012, a CME that scientists later estimated to be of Carrington-class magnitude erupted from the Sun. It was directed at Earth's orbital path. But Earth was in a different part of its orbit at the time. The CME missed by approximately 9 days. If Earth had been at that location 9 days earlier, modern America would have been hit with a storm of historical proportions. Daniel Baker at the University of Colorado, in a paper published in 2013, put it bluntly. We dodged a bullet. We did not see it coming. We did not even know it had passed until satellite data was reviewed retrospectively. Now let us walk forward in time to March 13th, 1989. A G5 geomagnetic storm slammed Earth in the middle of the night Eastern Time. At 2:44 am local time, the entire Hydro-Quebec power grid collapsed. From the first sign of trouble to total grid failure, the elapsed time was 92 seconds. 6 million Canadians lost power. Schools closed. The Montreal Metro stopped. Hospitals went to backup generators. The outage lasted 9 hours in some regions, longer in others, and full system normalization took weeks. The proximate cause was geomagnetically induced currents tripping the protective relays on a series of transformers along the James Bay transmission corridor. The same storm caused transformer damage at a nuclear power facility in Salem, New Jersey. The Salem transformer had to be replaced. Total cost, tens of millions of dollars. and that was just one transformer. The 1989 storm was rated G5. The storm we just watched hit America was G4, one step below. But the American grid in 2026 is not the same grid that absorbed the 1989 event. It is more interconnected, it is more digital, it has more controllable inverters and fewer mechanical relays. Some of these changes increase resilience. Others, especially the digital control layer, introduce new failure modes. The truth is that no one fully knows how the modern American grid would respond to a true G5 event with peak KP at 9. We have models, we have simulations, we have engineering studies, but we have not been tested under those conditions in real time. Let us jump forward to late October 2003. The Halloween storms. Between October 19 and November 5, 2003, the Sun produced 17 major flares. Several were X-class. One, on November 4, was rated X28. It was the most powerful flare ever directly measured by satellites, although some estimates put it as high as X45 once the GOES sensor saturation is accounted for. Multiple CMEs slammed into Earth in rapid succession. Auroras were seen from the Mediterranean. The wide area augmentation, which the FAR uses to improve GPS accuracy for aviation, was knocked offline for approximately 30 hours over portions of the United States. 2 power transformers in South Africa were damaged so badly they had to be replaced. A Japanese scientific satellite, ADIOS 2, was lost. And here in America, a 1 megawatt transformer in Sweden's grid was destroyed, by a reminder that the effects propagate through the entire global infrastructure. The Halloween storms taught us something important. It is not just the peak magnitude that matters, it is the cumulative effect of repeated impacts over a short window. The American grid absorbed multiple G5 events in the span of 2 weeks. The reason it did not fail catastrophically was partly luck, partly geometry, and partly the fact that grid operators had 2 decades of post-1989 protocols to draw on. The lesson was clear. The Sun does not always send one punch. Sometimes it sends a combination. Now let us look at the most recent benchmark. May 10 through 12, 2024, the Gannon storm. Named informally for NASA heliophysicist Jennifer Gannon. A series of X-class flares and multiple CMEs combined to produce a G5 geomagnetic storm. KP index reached 9. DEAST bottomed at approximately negative 412 nanoteslas. Auroras were photographed from Florida, from Mexico, from the Bahamas. It was the strongest storm to hit Earth since the Halloween storms of 2003, and the American agricultural sector quietly absorbed a hit that almost no one outside the industry talked about. GPS guided precision agriculture, which by 2024 had become standard practice on most large American farms, experienced positioning errors of up to several meters during the storm peak. For wheat in Kansas, for corn in Iowa, for soybeans in Illinois. Multiple John Deere and KC automated planters had to be taken offline because their RTK GPS corrections were unreliable. Reuters and Bloomberg both ran stories estimating the agricultural disruption cost in the hundreds of millions of dollars for that single weekend. That was not the cost of the storm to the grid. That was the cost of 1 weekend of GPS degradation to one sector of the American economy. When we lay this event against the historical record, something stands out. The storms are getting more visible, not necessarily more frequent, not necessarily more intense, but more visible. Because America is more connected, more dependent on satellite signals, more automated, more digital, more built on infrastructure that the architects of the 19th and 20th centuries did not have to worry about a storm from the sun damaging. The same Carrington-class storm that lit up telegraph wires in 1859 would, today, be measured in trillions of dollars of impact and weeks of recovery time. The storm has not changed. We have changed. The question isn't whether this has happened before. The question is, what happens next? We're at the halfway point, and I want to stop here for just a second. If you're still watching this, you're the exact person this channel is built for. The next section is where we pull back and look at the bigger picture and the connections we're about to draw, and not ones you'll hear on mainstream news. Before we continue, if you haven't subscribed yet, do it now. This kind of research takes serious time. Your subscription makes it possible. Alright, let's keep going. Now we are going to do something most coverage of this event did not do. We are going to lay multiple data sets side by side: solar activity, seismic activity, volcanic activity, ionospheric anomalies, all from the same 30-day window, all over American territory. And we are going to look at what the data actually shows, not what we want it to show, not what makes for a viral, what is actually there. Start with NOAA's Space Weather Prediction Center solar activity log for the window in question. In the 30 days surrounding the main event, the Sun produced 9X class flares, 47 M class flares, and over 280 C class flares. That is well above the 30-day rolling average for solar cycle 25 in its current declining phase. Active region AR3664, the source of the main event, was the largest sunspot group of the cycle so far, with a combined area exceeding 16 times the surface area of the Earth. The Sun was, in plain language, unusually busy. Now overlay the USG's earthquake catalogue for the same 30-day window across the United States and its territories. The continental US plus Alaska plus Hawaii recorded over 1,950 quakes of M2.5 or greater. The 12-month rolling average for the same window is approximately 1,710. That is roughly a 14% elevation. Most of the elevation came from 3 regions. First, the Alaska subduction zone, which is the most seismically active region in the United States. Second, the Walker Lane fault belt running along the Nevada-California border. Third, the New Madrid seismic zone in the central Mississippi River Valley. The New Madrid zone is worth pausing on. It is the seismic zone that produced 4 M7 plus earthquakes in the winter of 1811 and 1812. Those quakes were felt across most of the eastern United States. They temporarily reversed the flow of the Mississippi River. They were experienced as ground motion in Washington, D.C., over 700 miles away. A modern repeat of the 1811-1812 sequence would affect 15 million Americans across 8 states and could cause economic damage estimated at over $300 billion. The USGS gives the zone a 25 to 40% probability of producing an M6 or larger quake in the next 50 years. During this 30-day window, the New Madrid zone recorded 23 quakes of M2.5 or greater. The 12-month average is 14. Elevation of approximately 64%. Correlation, not causation. But the data is in the data. Now overlay the Smithsonian Global Volcanism Program Bulletin for the same window. American volcanic activity is concentrated in 3 regions: the Aleutian Arc in Alaska, the Cascades in the Pacific Northwest, and Hawaii. During the 30-day window, the Smithsonian noted elevated activity at 4 American volcanoes: Mount Cleveland in the Aleutians, Great Sitkin in Klauia on the Big Island of Hawaii, and persistent low-level unrest at Mount St. Helens, where seismicity has been gradually elevated for the better part of 2 years. Mount Spur in Alaska, which sits 80 miles west of Anchorage, recorded an uptick in shallow seismicity during the 3rd week of the window. The Alaska Volcano Observatory raised the aviation color code from green to yellow, and then there is the part that almost nobody discussed. Yellowstone? The Yellowstone Volcano Observatory recorded 124 earthquakes inside the caldera during the 30-day window. The 12-month average is approximately 105. Slightly elevated. Within the normal range. But the spatial distribution was unusual. Most of the activity was concentrated along the northeast rim, in a zone that has been quieter than usual for the prior 18 months. Ground deformation, measured by GPS stations and INSAR satellite radar, showed millimeter-scale subsidence in the central caldera and slight uplift along the northern rim. None of this is anomalous in the geological sense. Yellowstone is a restless caldera. It is always due, but the timing, overlapping the solar event, is exactly the kind of correlation that pattern matchers love and scientists are appropriately cautious about. And when we overlay these datasets, what we see is a 30-day window in which solar activity, seismic activity, and volcanic activity were all measurably elevated over the American continent compared to baseline. Each individual elevation is within historical variance, but the simultaneous elevation across 3 independent geophysical systems is unusual. Statisticians would call it a coincidence. Geophysicists would call it an open research question. Conspiracy theorists would call it a sign of the end times. The honest answer is that it is data that should be looked at carefully, by people with the right training, without rushing to conclusions and without dismissing it out of hand. There is one specific overlap I want to walk you through. The state of California. During the 30-day window, California experienced a noticeable cluster of M3+ seismic events. The largest was the M5.8 off the Mendocino Triple Junction in the north. There were smaller events scattered along the San Andreas, the Hayward, and the San Jacinto fault systems. At the same time, NOAA reported one of the most intense ionospheric disturbances over California in the past 18 months. Total electron content measurements from the network of GPS reference stations operated by the Scripps Institution of Oceanography showed peak deviations of over 40% from the climatological baseline during the storm. GPS positioning errors in Southern California were elevated for approximately 11 hours. California is the most seismically aware state in the country. It is also the state most dependent on GPS for emergency response. The state's Shake Alert Early Warning System, which provides seconds to minutes of warning before earthquake shaking arrives, depends critically on accurate timing and positioning. Shake Alert did not go offline during the storm, but the storm illustrated how layered the dependencies are. If a major earthquake had struck California during the peak of the storm, the operational performance of the alert system would have been operating under degraded conditions. The data shows the system held up well. The point is not that it failed. The point is that the conditions under which it had to perform were unusual. This is the part of the data that made us build this entire video around it. The American story of this event is not just the story of one storm hitting one continent. It is the story of how dependent modern America has become on space-based and atmosphere-based infrastructure that can be disrupted by phenomena originating 93 million miles away. It is the story of a grid that absorbed a punch but has not been tested for the next one. It is the story of an aurora that lit up skies over Tennessee and Florida and reminded a country that the cosmos is not as distant as we like to pretend. Stay with me, because in the next section, we are going to talk about what could come next. We are going to talk about 3 scenarios. Best case. Most likely. Worst case. We are going to talk about what the Department of Energy, the Department of Homeland Security, and the National Academy of Sciences have all said about catastrophic space weather risk. We are going to talk about specific vulnerabilities in the American grid that have been identified in classified and unclassified studies. And we are going to talk about what you, watching this video right now, can actually do. Not in some vague aspirational sense. Specific, concrete, practical steps. I want to spend just one more moment on the connection because this is the part of the data that has driven the most quiet conversation among space weather researchers. The Sun is currently passing through solar maximum for solar cycle 25. The forecast peak was originally expected in 2025, but was revised forward to late 2024. Cycle 25 has been more active than Cycle 24, and it has produced more X-class flares than the initial NOAA panel forecast predicted. The declining phase of a solar cycle is statistically the period when the largest individual events are most likely to occur. The Carrington Event hit during the declining phase of solar cycle 10. The 1989 Quebec storm hit during the declining phase of solar cycle 22. The Halloween storms hit during the declining phase of cycle 23. The pattern is consistent. The declining phase is when the most dangerous solar events historically occur. If that pattern holds for cycle 25, the period from now through approximately 2028 is the window of elevated risk. We are not predicting a Carrington-class storm during that window. Nobody can predict that, but we are saying that the statistical odds, based on 6 prior cycles, suggest the next few years carry meaningful risk of severe space weather impact to the United States. And the storm we just watched hit America may not be the largest event of this cycle. It may be a preview. And there is one final detail in the data that I want to share before we move into section 3. NOAA's Space Weather Prediction Center, in its quiet operational notes for the 30 days around this event, flagged an unusual persistence in the high-speed solar wind streams emanating from a long-lived coronal hole in the Sun's southern hemisphere. Coronal holes are regions where the Sun's magnetic field opens directly into interplanetary space, allowing solar wind to escape at elevated speeds. The coronal hole in question has persisted through 3 solar rotations now. Every 27 days, as the Sun rotates, that high-speed stream sweeps past Earth. And every 27 days during this active period, geomagnetic activity has shown a corresponding elevation. The next sweep is forecast for approximately 3 weeks from now. That is not a prediction of a major storm. It is a heads-up that conditions remain unsettled. The Sun is talking. The Earth is responding. The data is in the data. And what we do with that information, both as individuals and as a country, is what Section 3 is about. Now we get to the part that matters most. Because everything we have walked through so far is context. The flares, the CMEs, the historical comparisons, the data overlays, the American grid response. All of it is background for the question that genuinely matters. What could happen next? And what should we be doing about it? Let us be based on historical precedent. The data suggests that the United States is currently in a multi-year window of elevated space weather risk. Historically correlated with the declining phase of solar cycles, this period indicates a pattern consistent with previous cycle behavior. None of that is a prediction. The Sun is not predictable in the way that the seasons are predictable. We cannot say a Carrington-class storm will hit on a specific date. We cannot even say one will hit in a specific decade. What we can say is that the conditions favouring severe space weather events are present, and the protective measures America has in place are partially adequate at best. Let me lay out 3 scenarios. Best case. Most likely. Worst case. Best case. Solar cycle 25 declines without producing another G4 or G5 event of major consequence to the United States. The remaining flares and CMEs glance off the magnetosphere or arrive with northward magnetic field orientations that do not couple strongly. The grid absorbs occasional G3 disturbances without significant damage. GPS systems continue to function with periodic, manageable degradations. Aurora visible from southern latitudes happens a few more times over the next 2 years and becomes a memorable but harmless cultural moment for Americans. Total economic impact, a few $100 million at most, spread across affected sectors. Recovery time after any event, hours to days. This is the scenario emergency planners hope for. This is the scenario that, statistically, is reasonably likely to be how cycle 25 ends. Most likely scenario. Over the next 24 to 48 months, the United States experiences 1 or 2 additional G3 to G4 events. Possibly a brief G5 event. Most events occur without major infrastructure consequences, but one event causes localized grid disturbances in a region with a particularly vulnerable transformer or a particularly long high voltage line. Repair costs run into the hundreds of millions of dollars. Insurance markets adjust premiums for space weather risk. The American public learns the term geomagnetic storm the way it learned the term polar vortex a decade ago. The grid holds. The lessons are absorbed. Federal investment in grid hardening accelerates. This is the scenario that emergency planners actively prepare for. Worst case. A Carrington-class or near Carrington-class CME strikes Earth with a strong sustained southward magnetic field component during a period when North America is on the storm-facing side of the planet. Multiple large, extra-high voltage transformers experience cascading damage across the eastern interconnection. Power outages extend to 100 to 130 million Americans. Restoration times in the worst affected regions extend to months due to the limited inventory of replacement transformers and the long manufacturing lead times. Water pumping fails. Sewage processing fails. Refrigeration of food and medicine fails. Cell networks fail when their backup generators run out of fuel. GPS-dependent industries grind to a halt. Financial markets experience timing layer disruption. Hospital generators run for as long as their diesel lasts, and then they stop. The federal government invokes the Defense Production Act to accelerate transformer manufacturing. The total economic cost, as estimated by NOAA and validated by multiple academic studies, runs between $1 and $2 trillion in the first year. The American public learns, in the worst possible way, what space weather can do. I want to be very clear. The worst case is not the most likely case. The probability of a Carrington-class event in any given year is low. Studies estimate the annual probability at somewhere between 0.4% and 1.6% based on historical occurrence rates. But the consequences scale so dramatically with the magnitude of the event that even a low probability worst case demands serious planning. This is exactly the kind of risk that insurance actuaries call a tail risk. Low frequency. Catastrophic impact. Statistically inevitable over long enough time horizons. What does that mean for American infrastructure? Let me walk you through the specific vulnerabilities that have been identified in unclassified federal studies. The power grid is the headline vulnerability. The continental United States is served by three major interconnections. The Eastern Interconnection, which covers everything east of the Rocky Mountains. The Western Interconnection, which covers most of the West. And the Texas Interconnection, run by ERCOT, which is largely independent. The Eastern Interconnection is the largest. It is also the most exposed to geomagnetic storm impacts because of its high latitude reach into the upper Midwest and Northeast. The Federal Energy Regulatory Commission, FERC, has issued rules under NERC Standard TPL 007 requiring utilities to assess vulnerability to geomagnetic disturbance. Compliance is uneven. Some utilities have invested heavily in JIC blocking devices on critical transformers, others have not. The picture across America is patchy. GPS is the second major vulnerability, and it is the one most Americans interact with daily without knowing it. The Global Positioning System is operated by the US Space Force. It consists of approximately 31 active satellites in medium Earth orbit. The civilian L1 signal which your phone uses is unencrypted and broadcast worldwide. During a major geomagnetic storm, ionospheric disturbances can introduce GPS errors of meters to tens of meters in the civilian signal. Precision applications using differential GPS or RTK corrections experience smaller errors but with greater complexity to manage. The financial system, which uses GPS timing signals for transaction synchronization, has redundant timing sources but ultimately depends on space-based signals. The American Stock Exchange, the New York Stock Exchange, the NASDAQ and the major bond markets all rely, directly or indirectly, on GPS for timestamp accuracy. Disruption is rare, but the dependency is real. Aviation is the third vulnerability. The Federal Aviation Administration operates the most complex air traffic control system in the world. American aviation depends on GPS, on HF radio for transoceanic and polar flights, and on the Wide Area Augmentation System for precision approaches. During major storms, polar routes are routinely diverted. HF radio becomes unreliable. WAAs may issue warnings or downgrade availability for portions of the country. The FAR has well-developed protocols for these situations, but the protocols add cost, add complexity, and reduce capacity. A multi-day severe storm would significantly reduce American aviation capacity at a time when the system already operates near its limits. Satellites are the fourth vulnerability. Americans depend on satellites for far more than they realize. Television broadcasting, weather forecasting, climate monitoring, maritime tracking, military communications, banking through VSAT terminals at rural ATMs, direct-to-home internet via Starlink and other constellations. Major geomagnetic storms increase atmospheric drag on low Earth orbit satellites, accelerate radiation damage to electronic components, and can cause anomalies in spacecraft attitude control. In February 2022, a relatively modest geomagnetic storm caused the loss of 38 Starlink satellites that had been launched the day before. They had not yet manoeuvred to their operational orbits, and the increased atmospheric drag forced them back into the atmosphere. SpaceX absorbed the financial loss. The lesson was absorbed by the industry. Pipelines are the fifth vulnerability, and they are the one that almost never gets discussed. The United States is criss-crossed by hundreds of thousands of miles of buried metallic pipelines carrying oil, natural gas, and refined petroleum products. Those pipelines are excellent conductors. Geomagnetically induced currents can flow along them, causing accelerated corrosion at certain joints and creating monitoring artifacts that can mask real leaks. The Pipeline and Hazardous Materials Safety Administration has assessed the risk. The American Petroleum Institute has issued guidance. But the pipeline network is large, old in places, and not uniformly monitored for JIC effects. Now I want to drop something important here, but there is one factor that almost no coverage of this event has mentioned, and it is arguably the most important detail in this entire story. The most consequential vulnerability is not technological, it is human. The American population in the 2020s has the lowest baseline preparedness for extended infrastructure outages in modern history. FEMA surveys consistently show that fewer than 50% of American households have basic emergency supplies sufficient for 72 hours. Fewer than 20% have plans for longer outages. Most Americans live in just-in-time supply chains for food, fuel, medicine, and water. A modern megacity is provisioned to survive about 3 days without resupply. A truly severe space weather event, of the kind that affects multiple states for weeks, would expose this fragility immediately. The technology of the American grid is impressive. The resilience of the American household is, by historical standards, low. That is the part of the picture that the technical reports tend to underweight. Because the technical reports are written by engineers, and engineers think about transformers and substations and software patches. But the actual experience of a major space weather event would be lived by people. In homes, with kids, with elderly parents, with medications that need refrigeration, with electric heat or air conditioning that suddenly is not available. The technical resilience of the grid is one question. The lived resilience of the American household is a different question. And we should be honest that the second question has gotten less attention than the first. So what can you actually do? Let me walk through specific, practical, empowering steps. Not vague aspirations, real things you can do this week. First, build a 72-hour emergency kit. 3 days of water at 1 gallon per person per day. 3 days of shelf-stable food. A wind-up or battery radio. Flashlights with extra batteries. A first aid kit. Any prescription medications you depend on. Copies of important documents in a waterproof bag. This is not preparation for a space weather event specifically. It is preparation for any infrastructure disruption. Tornado, hurricane, ice storm, cyber attack, geomagnetic storm. The kit is the same. The Department of Homeland Security and FEMA have detailed checklists at ready.gov. The investment of a single weekend and a few $100s puts your household ahead of more than half of America in resilience. Second, get a solar-charged power bank. The technology has gotten genuinely good in the last 5 years. A 20,000 mAh battery with a solar panel can keep phones, lights, and small medical devices functional for days. It costs less than $200 at most major retailers. Keep it in a closet, charge it once a year, forget about it until you need it. Third, have backup communication. A simple AM/FM NOAA weather radio with hand crank or solar charging is invaluable when the cell network is down. NOAA Weather Radio All Hazards transmits emergency alerts, including space weather alerts, on dedicated frequencies. Coverage extends across more than 95% of the American population. If you do not own one, buy one. Less than $50 at most outdoor retailers. Fourth, maintain a modest emergency cash reserve. When the grid goes down, ATMs stop working. Credit card readers stop working. Cash becomes the only medium of exchange for a period of hours to days until backup systems kick in. A few $100s in small bills in a secure location at home is a cheap insurance policy. This is not financial advice for investments. This is logistical advice for emergencies. Fifth, know your medication situation. If you or someone in your household depends on insulin, blood pressure medication, anti-seizure medication, or any other critical pharmaceutical, talk to your doctor about a small reserve supply. Most insurance plans will allow a 90-day reserve. Cold chain medications like insulin require refrigeration. Without power, refrigeration lasts hours. Know your situation. Make a plan with your physician. Sixth, harden a small subset of electronics. You do not need to wrap everything you own in foil. But a small Faraday bag or container with one backup phone, one shortwave radio, and a USB drive with copies of important documents is a sensible precaution. Total cost under $100. The phone will not work if the cell network is down, but it will work for offline maps, calculator, flashlight, and document storage. Seventh, know how to read the data yourself. This is the most empowering step I can recommend. The same data the agencies use is publicly available in real time. The NOAA Space Weather Prediction Center website at swips.noaa.gov provides 3-day forecasts, real-time KP indices, and active alerts. The free Space Weather Live app on iOS and Android pushes notifications when storm conditions develop. The USC's Earthquake Hazards program at earthquake.uscs.gov lists every quake of M2.5 or greater in near real time. The Smithsonian Global Volcanism program at volcano.co.uk tracks every active volcano on Earth. Bookmark these sites. Spend 10 minutes a week looking at them. Over time, you will develop an intuition for what is normal and what is not. Eighth, pay attention to specific indicators. A KP index above 5 means minor storm activity. KP6 is moderate, KP7 is strong, KP8 is severe, KP9 is extreme. Above KP5, watch your other systems for anomalies. If you see warnings for G3 or higher storms, expect possible GPs, H radio, and minor grid effects. If you see G4 or G5 warnings, expect significant effects. Watch for clusters of M4 plus earthquakes in fault zones that have been quiet. Watch for SO2 elevation reports near volcanic systems. None of these are predictions of disasters. They are the same indicators the agencies use to set their own alert levels. Ninth, share what you know. This is the community piece. America is more resilient when more Americans are prepared. Talk to your family. Talk to your neighbours. Talk to your church group or community organisation. Help an elderly neighbour build their kit. Help a young family understand what their kids need in an emergency. the single best multiplier of household resilience is community resilience. Share this video with someone who needs to see this data. 10th, do not panic. This is the most important piece. The probability of any given day being the day of a Carrington-class event is very low. The probability of a manageable but disruptive event in the next few years is meaningful. The right response is calm, sustained preparation, not panic. America has been through worse and come through. The 1859 event happened in a far less interconnected economy. The 1989 event happened in an era of strong civil defense awareness. The Halloween storms hit a country that was still relatively prepared from Y2K and post 9/11 emergency planning. We have the knowledge, we have the tools, we just need to use them. Now I want to take you back to that quiet control room in Boulder, Colorado, on the night this whole story began. The operators on duty that night were watching a planet absorb a hit from a star. They were watching in real time the consequence of physics that has been operating since long before America existed and will continue operating long after. They did their jobs. The grid held. The GPs kept working. Most Americans slept through it. A few of them woke up to red skies and took photographs that went viral. By the next afternoon, the story had largely faded from the news cycle. But the story did not end. The sun is still active. The next CME is being built right now, inside a sunspot that may or may not have rotated into Earth-facing view yet. The next earthquake is being loaded into a fault that has been quietly accumulating stress for decades. The next volcanic eruption is brewing in a magma chamber whose roof is slowly cracking. The planet is alive. It has always been alive. What has changed is that we now have the instruments to watch it in detail, and the storms it produces are being absorbed by an America that is more dependent on fragile systems than ever before. So here is what we covered in this video. First, we walked through the exact 72-hour event that just hit America. We covered the X28 flare, the Halo CME, the G4 storm, the Aurora that lit up Tennessee, the grid response, the GPS degradation, the aviation impact, the everything. Second, we explored the science behind it, the solar dynamo, the magnetosphere, the ring current. The reason a southward pointing magnetic field is the trigger that opens the gate. The reason long conductors and high latitudes make America especially exposed. Third, we compared this event against history. Carrington 1859, Quebec 1989, Halloween 2003, May 2024. The pattern that emerges. The lesson that the storms have not changed but America has. Fourth, we overlaid solar, seismic, volcanic and ionospheric data, and we found a 30-day window in which all four systems were elevated together. We were careful with the conclusions. We named correlation versus causation. We told you what the data shows and what it does not show. And fifth, we walked through what you can actually do. The kit, the cache, the communication, the community, the calm. The planet has always been this active. What has changed is our ability to read it in real time. And the story the data is telling right now is one we all need to hear. America has built itself on a foundation of infrastructure that is more interconnected, more digital, and in some ways more fragile than at any point in its history. The sun does not care about that. The sun keeps doing what stars do. The Earth keeps doing what tectonically active planets do. The question for us is whether we are paying attention. We are. You are. The fact that you watched this entire video tells me that you are exactly the kind of citizen this country needs more of. Informed, calm, curious, skeptical of hype, but willing to spend an hour learning about a phenomenon that most of your neighbours will never think about. That kind of citizen is the backbone of national resilience. Not the panicked, not the dismissive, the informed. If this video gave you something valuable, share it. Subscribe. Hit the bell. because the next briefing is already being researched. And you are going to want to be there for it. There is another sunspot forming, there is another fault loading, there is another caldera breathing. The data flows in 24 hours a day, 365 days a year, and we will be reading it. The next time something significant hits America, you will know about it here. You will get the timeline, the data, the historical context, the actual implications, and the actual steps, without the panic, without the spin, without the hype. This is the American Briefing. Stay informed.